All right, so the topic of today is the Hill-Yoshida theorem. So what is the Hill-Yoshida theorem? So first, we need to define the resultant set of an operator. So in general, this is the definition, right? So this is really this is a generalization of matrices. So so for matrices, you have the eigenvalues, eigenfunctions, and so we try to do the same with operators, with linear operators. And so, but since we are working in infinite dimensional setting, some things are different. For example, for a matrix A, the matrix A is invertible if and only if when you look at A minus lambda I, the determinant of this matrix is non-zero, which means that the subset of eigen vectors is reduced to to zero, right? So all right, and so you have this definition. So because we work in infinite dimensional setting, so that's the general definition. So the resultant set is the set of all complex numbers, and we call it regular values for which. So here you see the analogy with the matrix is the same. When you know that, you look to the eigen vectors is 1-to-1. So 1-to-1 means injective. All right. So if I work with in finite dimensional setting, this is it. All right. So in finite dimensional setting, you only have two cases. Is that if lambda I minus r is injective, then you don't have eigenvectors associated with the eigenvalue lambda. So lambda will not be an eigenvalue, and onto means surjective. So the range of lambda I minus a is the whole set. But in infinite dimensional setting, you need to define put those as conditions. So we call regular values if lambda I minus a is 1-to-1 or injective, onto means surjective, and furthermore, so now you can define the inverse is continuous or bounded from x to x. Sometimes in some books, you can find a different definition for that. And so I suggest you to look about it. So when R is closed and the range of lambda I minus a is dense in X, then you can then if lambda I minus A is 1 to 1, and if then you can drop off the onto condition here, right? So, okay, I'm not going to do much more details about that. So, but I can refer you to there's an excellent book on PDEs about from Rinaldi and Rogers, and you can look. There's a good stuff about. There's a lot of books about that, but this one is yeah, is interesting. Okay. Also, you have this exercise. So these are suggestions. I'm not going to correct those, but it's a good exercise to think about it and to try to solve it. If A is densely defined and closed, then the resolvent set is an open set. All right. So why I say that? Because to state the Yoshida theorem, you need the resolvent set. Okay. So that's why I need this definition here. All right, so let's go and let's deal with the Hill-Yoshida theorem. So, in fact, what does the Hill-Yoshida theorem do? It gives a necessary and sufficient condition for an operator A, a linear operator A, to be the infinitesimal generator of a C0 semigroup of contractions. So pay attention to its semigroup of contractions, okay? And so this is equivalent. You need two things. First, A is densely defined and closed. And the second thing, the resolvent set of A contains the positive half line, positive real half line. So the real numbers that are between 0 and plus infinity. And furthermore, for each of these lambda, you have that R of lambda A, this norm, okay, this is bounded. We know that by definition of lambda in the resolvent set, lambda is bounded. But you have that, in fact, it's bounded by 1 divided by lambda. So we will see today the necessity, meaning that how these conditions come from. So this is an interesting stuff. So if you have a semigroup of a C0 semigroup of contractions, then these two things are verified. We are going to see that today, right? And so next week we are going to prove and see why, if those two conditions are true, then A generates a C0 semigroup of contraction. So we are going to give the proof of the Hill-Yoshida theorem, and today the necessary part. So so first we need to prove that if A generates the C0 semigroup, then A is densely defined and closed. Well, we already did that. Okay, we did that in last time in the theorem. Okay, so this is already, we already did it. So let's just recall why. So the first necessary condition of the Hill-Yoshida theorem is written here. And so why dA is dense in X? Because when you define this integral, we proved that this is in dA. So when epsilon goes to 0, this is a classical formula. This goes to X. So you have that for each X in X, you can approximate X by a sequence in D of A, thanks to this argument, right? So after that, I'm not going to do the proof again, but you can also prove that A is closed with this. Again, we proved these things. So now, next we are going to prove the point 2, and in order to do that, we will define this quantity. This is kind of the Laplace transform of ST of X, and so we define for each lambda, we define R lambda of X as the integral between 0 and plus infinity of this thing. So first of all, let's prove that this is well defined. So in order to do that, I just take the norm, and so I know that this quantity is less than the integral of the norm, which is less than the norm of ST of X dt. But since ST is a C0 semigroup of contractions, this is less than this. So the norm of S of t is less than 1, because S of t is a C0 semigroup of contractions. So then this is nothing that is, which is equal to norm of X divided by lambda.
Vous avez oublié, monsieur, moins W, c'est prononcé moins W dt, non?
No, because S of t is a semigroup of contractions. So the norm of S of t is less than 1. Your remark would be true if ST was a general semigroup, C0 semigroup. In that case, you have that S of t in norm is less than m exponential omega t. But here I have S of t less than 1 because it's a semigroup of contractions. This gives two things. So this gives the existence of the integral, and also here I have that the norm of R lambda is bounded by 1 divided by lambda. So the next and final step, in fact, for the proof of the necessary condition, we want to prove that, in fact, in fact, R lambda is the inverse. So is R of lambda A. Yeah, there's no coefficient between R lambda and R lambda A. It's a usual notation, and in fact, they are the same, but we need to prove it. And I recall that this is lambda identity minus I minus A minus 1. So let's do that. So first, we want to compute, and this is an exercise. So we need first to look at SH of R lambda minus R lambda and X here. For all fixed X in X, we want to look at this quantity, this limit Y. If this exists, then this means that R lambda X belongs to D of A, the domain of A. And if we can compute this explicitly, we will have this will give, if this exists, this will give A of R lambda X, if this limit exists. So as an exercise, I propose to try to compute this limit. Try to do that. So we are going to do this computation. So let's first compute. So forget about the 1 divided by h, and let's focus on SH R lambda of X minus R lambda of X. So this is by definition S of H applied to exponential minus lambda t st x dt minus okay, so what first I can put that inside? You agree, right? I would put the S of H inside. So this will be equal to the integral of exponential minus lambda t times st plus h x dd minus, so the same thing, but we've just all right, you agree? Just I use the properties of the semigroup. So S of H applied to S of T is S of T plus H, right? So next we are going to make this change of variable. So I will call this one T prime. And if I do that, I will obtain that. So SH R lambda X minus R lambda X equals so okay, I write it again so this will be more clear. So this is exponential minus lambda TST plus H X T minus integral exponential minus lambda T S of T X dt. Okay, and now I do T prime equals t plus h. So I get, so when if t starts at 0, t prime starts at h. And so t equals lambda t prime minus h s t prime x dt prime equals d t minus this one. I don't touch it, right? Okay, now I forgot about the, let's forget about the t prime. And what I'm going to do now is I want to start at 0 because there's they are similar. So I want to start at 0. So I start at 0. I start at 0. But if I start at 0, I need to take out the integral between 0 of h of the same thing. So sorry, this is a h here. This is h here. Of the same thing. And this one too. And so let's see what we get now. All right, so I will write it this one and this one. I write it like that. I can take out exponential lambda h. This doesn't depend on t. Minus 1. And here I have that. So I took here these two. It remains I need to keep this one. So I can take also this out here. Okay, let's comment here. Here I recognize this is r lambda, right? This is r of lambda. Okay, and of course I forgot here. There's a minus here. Okay, so I need to divide that by h and make IH converge to 0. What do I get? So next, I'm dividing the last line by h, and I want to look at what I obtain when h goes to 0. So I get that this is the limit when h goes to 0 of. So I have exponential lambda t minus 1. That's a h here. H. This term is r lambda. I wrote it. Minus exponential lambda h divided by h. integral between 0 and plus, sorry, h, this is h now, of all right, so when h goes to 0, what's that? So this is the nothing but the derivative of exponential lambda t at t equals 0. So the derivative of that is lambda. So here I forgot the x. This is lambda, and our lambda x doesn't depend on h, so I obtain the same. And here, so again, this I know this stuff. So when h goes to 0, the integral between 0 and h divided by h will give me the value of this at time t equals 0. Yeah, and so what's that? So this is the value of this thing at t equals 0. So what do I get? So if I take t equals 0, this is 1. S of 0 is identity, so I get x. So this thing converges to x. All right, so any questions? So we're almost done. Okay, we're almost done. Why? So this is the definition of the points that belong to D of A. So I found that for every x in X, this limit exists, which means that R lambda x belongs to D of A, and furthermore, that A of R lambda x is this limit. So from which, so what do we get? We get that A R lambda x equals lambda R lambda x minus x. What do you conclude from that? So this gives that x equals lambda I minus a r lambda x, which is exactly the same thing to say that lambda I minus a r lambda equals identity. Okay, so we proved that r lambda is the right inverse of lambda I minus a. It remains to prove that also we have r lambda times lambda I minus a is also identity. And so to do that, we need to, let's compute R lambda A. Try to get an expression from this one. So you replace R of lambda by its definition and try to get something. So by definition, this is the integral between 0 and plus infinity of sorry. So for all x here, for all, I will compute that for all x in D of A, right? I need to have the right to write A of x. So for each x in D of A, so now I just write the definition with A of x. So this is it. Okay, so we've seen that this one I can change. I can do that. We saw that. And here, what do I recognize here? This is very classic. This is classical. It's like an ODE with a matrix. So here, this is nothing but d. I take the derivative with respect to t of st of x. We've seen that. We proved that already last time. Okay, so now what can I do? Integration by parts. So can you compute that by integration by parts? Okay, so now, yes, I will do an integration by part. So I have that R lambda A x equals, so it's, yeah. So the integral between 0 and plus infinity of exponential minus lambda t d dt stx t. So yes, by integration by parts, this is minus lambda minus this is nothing but lambda, and here I get R lambda x, and here, so in plus infinity, again, as the S of t is a semigroup of contraction. So if I look at the norm of this thing, because norm of st is less than 1, norm of x is a number, this goes to 0 as t goes to plus infinity. And at t equals 0, I get x. So finally is that. So this gives x. We obtain x equals lambda r lambda x minus r lambda x equals r lambda minus identity x. So this gives R lambda minus. So sorry. Oh, what did I do here? Let's yeah. So yeah, I did forget the A here, so I put it again. So this is equal now to lambda identity minus A. So sorry. So this gives R lambda times lambda identity minus A equals identity. And done. So this ends the proof of the necessary part of the Heil-Yoshida theorem.